All right. So let us begin with the content for the lecture 8. And here the focus will be entirely on trying to work with LMIs in control. Okay. In particular, we will try to go to control design, then to robust control design. That will be our aim for the lecture. So let's get right into it. So first of all, remember what linear matrix inequality is. It's just a statement that some matrix is positive definite, for example. Okay. So the first example that we saw last lecture, when we were discussing usefulness of this approach, was that given matrix A, if we can find such positive definite matrix as that AS plus SA is negative definite, we have proven continuous time stability for the system x dot equals to AX. Okay, so given this approach allows us to solve for stability equations. That is what we saw last time. Okay, good. Nice, easy. Now let us consider the system with control U. Now we'll see the derivations of those things. So let's say we have control U equals to Kx, right? Let's have system x dot equals to Ax plus b, control U equals to Kx. And we have a Lyapunov function V equals to x s x, with s being positive definite. Okay. So the system becomes, after we substitute control, the system becomes x dot equals to a plus bkx. Notice plus, not minus. Why plus? Well, because convention. In this case, we don't have minus kx, we have kx, so no minus. Now let us find derivative of this Lyapunov function, time derivative. Okay. Well, time derivative would be x transposed. Sorry, x dot transposed cx, which is here, plus x transposed c x dot, which is here. Notice that this part is x dot, this part is x dot. Okay. So this is just x dot transposed. Okay, thank you. All right, so this is just a v dot. Again, how it's defined v dot? Just differentiate each part. We have we can think of it as x times sx. S is a constant, so s doesn't have a derivative. So x dot times cx plus x times cx dot. Good. Now this thing can be rewritten as an LMI. In order to rewrite it as an LMI, we just first we observe that this function will be negative definite if this matrix is negative definite. So this is a quadratic form. It will always be negative if the matrix of the quadratic form is negative definite. However, here we have a problem. This is not linear in decision variables. Like these decision variables enter the equation quadratically. So they multiply each other. So it's not linear. It's not linear matrix inequality because decision variables enter into it quadratically. All right. So far we cannot solve it as an LMI. This is not an LMI. So it says LMI, it's not. It should be just matrix inequality. It's not LMI. Not linear decision variables. Okay. Do we have questions so far? Like about the steps we took? Lyapunov equation, closed loop system with control Kx, found derivative for Lyapunov equation, observed that the matrix of the quadratic form have to be negative definite. All right, assume no questions. Then next, what we do is a very typical step in the derivations. We introduce new variable p, which would be S inverse. Okay. And we multiply the original equation on both sides. Why can we do that? Well, we can do that because there is a property called Congruent Transformation, which says if we multiply a matrix by m transposed on both sides, and if M is 4-rank matrix, then you don't lose definiteness. So positive definite matrix multiplied by M transposed on left and right is still a positive definite matrix. You can prove it by just saying x, p, x. I mean, let me just show you very quickly how the proof works. We probably have it in appendix, but let's just quickly show you how the proof goes. So if you have x dot e x negative definite, let's say, and what we want to prove is that x m p m transposed x would also be negative. Or let's just put for prettiness like this. Okay. So we want to prove that there is an implication that this implies this. Okay, that's what we want to prove. Right. If it is, but since it is 4-rank, it would also, there's a two-way implication because you can always multiply by inverses of those matrices and it would be the same. All right, so let's prove it. Well, the way we prove it is we introduce new variable y, which is equal to mx. And in this new variable, we have a expression m transpose y transpose py, which we know that would be negative because p is negative definite, so y py would also be negative, right? And y, since m is square and 4-rank matrix, y and x both there is one-to-one correspondence between y and x. So for every y, there is a corresponding x, and for every x, there is a corresponding y. So that means that we would never be able to find such x that would make this equation positive or equal to 0 outside of 0 x. Because otherwise there will be a unique y corresponding to this x, which would break this equation, which is impossible. So this is how we can prove that you can multiply positive definite matrix on both sides by, let's say, m transposed without losing positive definiteness. Again, this procedure here is useful to know. It's just how you prove those things, like changing variables and look at the definition. Okay, so we can multiply this equation. Let me clear everything. This equation we can multiply it on both sides by p, which is S inverse. What happens when we multiply it by p? Let's multiply it here. Let's say we multiply it by p. Why not p transposed? Well, because p and p transposed are equal to each other. P is a symmetric matrix. Since S is a symmetric matrix, its inverse is also symmetric, okay? So we don't need to actually transpose anything here. So we have P, and another one here, P, and P. Now what happens is these guys cancel each other because it is S times S inverse, P is S inverse, so they cancel. And here's the same thing. Right. And remember that there is a transpose here. So yeah, but that we'll see on the next slide. So this is what happens. P, basically S was on this side, on the right, it will be on the left. Here S was on the left, it will be on the right. So that is ultimately what we achieved. Just change sides of the variables by this multiplication. Again, something you can remember, if you want to change size of the variables, you can multiply on both sides. Okay, let's see what we got. This is what we got. Next, we introduce a new variable L equal to KP. KP, this will be L now. P times K transpose times B transpose will be now L transpose B transpose. So the LMI now becomes this. So let me highlight. Like this became L. This became L transposed. And the rest is kind of the same. So this now is LMI. And this can be solved in the SDP solver. So we achieved it. This is control design. And this is how to get a controller. Controller, you get it using K equals to LP inverse. LP inverse. And we don't need to go back to our original variable S because we're not using it anywhere. So we don't have to go back. We were just using it for the derivation. But this is perfectly good. K is perfectly good. Right? Any questions about what we just saw? About this derivation? Right, no questions. No questions. Okay, it's going to be tougher next because this is so far very simple. We only used how many tricks we used? We used, I mean, this is not even a trick, this is just definition, I'll say. One trick, change of variables and multiplication on both sides. We'll call it one. Another trick was change of variables here. And so I guess change of variables, congruent transformation, and change of variables again. So three operations, and all of them very basic. Okay, good. Next time will be more. Now consider the case when x dot equals to ax, but you don't know a exactly. So you don't exactly know a. You have uncertainty. So, for example, you don't know mass exactly. Maybe your drone lifts like a parcel, but the parcel is plus or minus 10 grams. Okay. Friction may be unknown. All kinds of things are not really known. So it's typical. All right. So the way we can write this model is we say here's A, and here's like uncertainty matrix basically. This is like delta A. So this is kind of like component of A, which is unknown. F and E are known matrices here. So F and E are matrices that you know. Okay. They model uncertainty. Okay. They model uncertainty. So they show where uncertainty lies. Delta, on the other hand, is completely random. Delta is completely random. You don't know what it is random. You don't have information about delta. The only thing that you know about delta is that it is norm bounded. The norm of delta less than 1. Delta is a matrix, is a matrix of the dimensions defined by F and E. But delta is also norm bounded. In which sense this norm is? Well, it is a matrix norm, so it would have to be one of the known matrix norms. Later in the derivations, you will see exactly what this norm is. But I think it is fair, I have to go by my memory, but as far as I remember, it is a second induced norm. So it's norm induced by the vector norm 2, which is, I believe, spectral norm. So, probably for most of you doesn't say anything, so whatever. It's just a matrix norm. We will see the properties of this norm in a bit when we go through the derivations. But point is, it is a matrix, which is, it can achieve any value, but the norm of the matrix has to be less than 1. Okay. You will see in a second what this means, norm less than 1, when we derive control. Okay. Do we have questions about what we see here? This is an uncertain model with model uncertainty, with uncertainty in A matrix. It's very typical. All right. So let us write a Lyapunov equation for this system. So what we have is this is derivative of the Lyapunov equation. Derivative of the Lyapunov equation. And here we have, this is x dot. This is x dot. You can see the difference is just that A, it's now not A, but A plus F delta E, F delta E. Now let us introduce new variable delta EX, that is a new variable. We'll call it now, omega. Okay, omega. I'll use slightly different color code. Okay, so now where is omega? Omega is here, and omega is here. So this is omega, this is omega. Okay, so A, x times A times SX, x times S times A times X, those are the same as before. So let us note that this, I'll show it somehow like this. This is exactly the same as before. This component did not change from previous formulation. But now we have this additional component that did change. And this additional component has omega here and here times F S X X S F. Okay. Good. So this is a LMI so far with respect to S. The only problem is that it has two variables. So we cannot, it's not LMI, it's like a quadratic form. We cannot just directly, I mean, we could write it as an LMI. It would be quite easy. You can imagine it will be, we'll see it in a bit. We'll see it in a bit. But it can be written as a quadratic form. It will be actually linear with respect to decision variables. The only problem is that we don't know what omega is. Okay, omega is not an independent variable. It depends on x. So it's a little bit tough. Okay, good. Now, in order to understand how omega behaves, we can look into this expression. What is omega times omega? What is omega times omega? And omega times omega comes from here, from this expression here. It is in fact x e delta times delta ex. Okay. And now we understand. We have a chance to understand what this constraint was all about. These constraints make it possible for us to say that omega times omega is less than xe times e times x, because this expression is bigger than this expression, where we have at the center delta, whose norm is less than or equal to 1. So in fact, what delta is supposed to be, it is supposed to be the kind of matrix which would make it possible for xe delta delta ex to be less than or equal to xe ex. Okay. So this is the definition of the norm, basically. It has to be the type of norm which would make this possible. And in this case, it will be induced second norm, I believe. Like it will be a matrix norm induced by the second vector norm. Okay. Good. Well, this is the only property of the norms that we're using in this derivation. Now, let us carefully look what we achieved. We achieved that v times v is less than x e ex. This is inequality. And we have this guy. That is also inequality. So we have two inequalities that involve two variables. And in fact, here comes the punchline. Let me clear everything. So this inequality needs to hold only when this inequality holds. Okay. So it doesn't need to hold always. It only needs to hold when this inequality 9 holds. Because asking it to hold always is too much. Basically, you're saying no matter what omega is, so no matter how bad the uncertainty is, you should always hold. Impossible, impossible. Your drone is not going to fly when your uncertainty in mass is 200 kilograms. Not going to fly at all. Okay. You cannot expect stuff like that. But you can expect that it would fly if the uncertainty in mass is very small. And the way we say it is that when v is less than or equal to x EEX, okay, when x dominates over omega. Sounds great. Sounds great. So all we need to do is to somehow express as LMI the condition that this expression 8 holds only when 9 holds. Okay. Now there is a way to do it. That's kind of fascinating that it is possible. But before we do it, let us just express those things. So this condition, we can rewrite it this way. Okay, this is the same thing, just rewritten. Now we can rewrite this further as this like quadratic form. So you notice that here x and x becomes this x. Omega becomes this omega. We have identity from the omega, and we have e times e from x's. And if you multiply it, it will become the same. Right. The same way, we can rewrite this expression here in terms of those variables. So we will get x omega equal to this guy and this guy. So it is possible in both cases. Okay, good. Now, somehow we need to find a way to make sure that this holds as long as this holds. How to do it? Well, there's a magic tool. When I say magic, I mean it's just math, but it is so fascinating. It's like absolutely non-intuitive to do it. So the process is called S procedure. Okay. So if you have positive gamma, positive scalar gamma, and we have m plus gamma n, let me color code it properly, n plus gamma n being negative definite. So gamma is positive, and this whole thing is negative definite. M plus gamma n. So this compound matrix is negative definite. Then it would imply that this z and z quadratic form being positive definite is implying z times m times z is negative definite. I'm sure even what I just said was difficult to parse. Okay. Let's try one more. So what we want is to imply that as long as this holds, this holds. As long as this is positive, this is negative. Okay, that's what we want to work with. As long as this is positive, this is negative. Good. When will this be true? It will be true if we can find positive gamma and negative definite m plus gamma n. That's all. We just need positive gamma and negative definite m plus gamma n. That's it. And that's what we want to do for our system. So let me just show you how it's used. We'll go back. So the way it is used is like this. We take this guy, this matrix. We have to add to it this matrix times gamma, times gamma. Gamma has to be positive, and this whole thing would have to be negative. This matrix itself has to be positive and negative indefinite. Let me just double check. I think it should be positive, but now I have fear because this doesn't look to be positive, so definitely this minus is scaling. Right, we'll double check the minus sign here. This minus sign makes me scared, but this minus sign makes me scared. So double check before you're going to use it. Double check the proof, okay? Because I'm pretty sure about this being positive. All right, good. Yeah, because I'm like. Okay. Okay. So the game is to take this original matrix, for which we want to make sure that it's negative, as long as this positive quadratic form is positive, right? This quadratic form has to be negative, while this quadratic form is positive. Okay. Okay. Yeah. By the way, maybe I was just wrong to say anything about this minus sign. Okay, let's stop talking about. So what we do is we get this matrix, add to it this matrix with multiply by gamma, and we insist that the whole thing is negative definite. So let's look at it. And what we get is this guy. So the original matrix is here. You can see that was the original matrix. And the addition is here, gamma EE minus gamma I. That is the additional matrix. In LMI form, this becomes okay. So in LMI form, what we get is a negative semi-definiteness condition. Good. Now, this is a condition of how to check robustness. That is not a condition of how to design a robust controller. Okay? Because there is no controller here. It is open loop. Let me see if we have a slide on how to design a controller. Yeah, next slide. Okay. So, so far, any questions? So what we did is we added one condition so far, one trick as procedure. Extremely difficult and important, but as a conceptually difficult. But we need to know it. It's a good thing to know. Right. Now let us consider the system where we have uncertainty in A and additionally B matrix. So we want to design control. Now we design control law as Kx. So the closed loop becomes A plus B plus uncertainty part here, F delta E. we already have seen the derivative of Lyapunov equation one more time with x dot. This is x dot. X dot transposed x dot. We do exactly the same thing. Introduce change of variables. Omega equals to delta EX. We have omega here, same as before. Everything else stays the same. This part stays exactly the same as before, as in the original derivation. Next, what we do is we rewrite this as a matrix. So this is the parts in front of X. Okay, they go here. This is the part in front of omega and multiplied by X. So this goes here. This part goes here. And there is nothing in like, there is no part where you have omega squared. So this is it. All right. This equation needs to hold for omegas which are equal to delta EX. Okay. From this follows exactly the same chain of reasoning. So we want this to be true, right? So we want this to be positive. And using as procedure, we add to the original matrix this new matrix. So the original matrix is this guy, this guy, and this guy. The new matrix that we added is this guy. Let me use same color coding. This guy and this guy. So this is what we added. Okay. And you can kind of recognize where it comes from. Here and here. And gamma is from the S procedure. Okay. Okay. Now this is nice, but we'll have trouble with this gamma. Because gamma is trouble. So we have, like, the better policy is to get rid of gamma. And there is a way to do it. Since it is a positive number, we can divide everything by gamma. We divide everything by gamma, and we introduce new variable C gamma equals to C divided by gamma. And in terms of C gamma, you can see this will become a C gamma if we divide everything by gamma. This will become C gamma. This will become C gamma. This will become C gamma. And we don't have any C. We don't have any standalone C. Only every C becomes a C gamma. So the equations then become like this. Identity here, E here, no gammas. Yeah, so that is another trick. Divided by gamma is another popular trick that we use. Now, we'll have to use Schur complement on the next stage. So here is a description of Schur complement, but now in terms of negative definiteness. The description is this would be a negative definite. This would be negative definite as long as this is negative definite. Okay. Those are equivalent as long as this is true. Okay. Good. Now, how are we going to use Schur complement? We have this expression, but like one of the one of the problems we have would come from having this guy here. Why? Well, because what we'll eventually want to do is multiply this on both sides by p. So we want to multiply it by p here, by p here, by p here, by p here. And if we multiply on both sides by p, we will have here p squared. That's not what we want. So we want to get rid of this E transpose E. All right. How do we do it? Well, this guy is the same as this guy. This looks bizarre, but they are the same. So what it is E times identity times E, which is indeed E squared, same as here. We have two minus signs, a minus sign here, minus sign here. They cancel. And we have identity inverse, which is just identity, so it doesn't do anything. All right. But this is a sure complement. So now we have this block. This is a standalone block in the sure complement. Here it is. Remember, sure complement allows us to have the string where we have A minus B, C inverse B transposed to transform it into a matrix. So sure complement allows us to construct a matrix out of a something with like transpose times inverse times transpose. Oh, sorry, B times inverse times B transposed. So it allows us to construct a matrix. So here, what we can do is we can like this becomes this part. This is like B transposed. This guy becomes this guy. This is B. And this becomes this. That is your C. So this is C inverse, and this is C. This minus, as usual, goes away because it is part of sure complement. And if this is negative definite, then this will be negative definite if this is negative definite. Minus I is always going to be negative definite. That is just absolutely true. Okay. Okay. Now, this is still not a solution because it is still not linear decision variables. We still have decision variables here multiplying each other. Okay. Well, let's finally find a solution. We, as before, introduce this new variable P that is C gamma inverse. And we multiply on both sides by this huge matrix PII. It is symmetric, so PII transposed equal to PII. And why is this II part? Well, because those blocks, how should I put it? Because these guys don't need to be multiplied, and these guys need to be multiplied only on one side. So that's why II. So when we multiply by PII on both sides, let me go to the previous slide and see what's going to happen. When we multiply, what's going to happen is here it will be multiple on both sides. It will be P. And hence here, this guy will cancel, this guy will cancel. Here it would be P would be only here on this side. So, and here P would only be on this side. Y just verify it by multiplying. So this cancels, but we'll have additional P in front of E here and here. In front of E here and behind E here. So this is what's going to happen. Well, let's see if this is indeed what happens. Yep. EP, PI. Okay. So finally introducing the L equals to KP, we know that this guy here becomes this guy, and that's it. And this 24 is the expression linear decision variables. So this is an LMI, and we can solve, put it into SDP and solve it. Notice it doesn't include gamma, doesn't include C. It has only P and L as decision variables. The only difference from before is that the matrix is bigger, and we have this those components here, and these components here. That's the bigger difference. While this guy, it remains absolutely the same as before. Do you have questions? Do you have questions about this monstrosity? Was it too much? Was it too much math for one derivation? Yes, do you have questions or comments?
It looked like we should reread it at least twice. It's not too much, but it's hard to understand in one reading.
Absolutely.
Maybe later it's will be more questions after I read this. Okay. But currently I can't say anything.
No, fair enough. No, I mean, when I was studying it on my own, I didn't get it from the first time. So it's, neither did I get it on the second time. So for me, it was more than 2 readings. So, but I'm slow. Okay. Yes. This is tough. This is complicated, but it works. You can implement it very easily in Python with CVX, and it will work very well. Okay. So this is how you can do a robust control design with continuous time systems. I didn't show you control design with discrete time systems. You can do it very easily. You have to use sure complement. So let me just go back a little bit. So remember good days when we only needed this as a control design in the beginning of the lecture? So for discrete systems, you cannot do this because your discrete Lyapunov equation looks like A, P, A transpose plus what? Plus P or minus P less than or equal to 0. Because it is already has 2 state matrices multiplying both sides. When you go from A to A minus plus BK, you would already have a quadratic term there. So you would already need to use sure in order to derive discrete control LMI. Not very difficult though. Like using sure is not very difficult, and it's not very difficult derivation. Doing robustness in discrete systems is non-trivial. So I don't know derivation for discrete if it even exists. I seem to remember reading a phrase somewhere that discrete, at least some kind of discrete robust control is impossible to derive as an LMI. Maybe I'm wrong, but definitely not easy. Definitely not easy. Right. So for discrete systems, it is more complicated. But for continuous time systems, that's what we have. Now, there is a way to do all of this simpler. And that is quadratic stability. So quadratic stability is the idea that you have, let's say you have this system, right? And this system is given as a linear combination of n systems, where those are convex combinations. These are convex coefficients. So lambda alpha I is bigger than 0. Sum of all lambda i's is 0. This is called a convex combination because a combination like this would turn you from vertex to to the interior of the polytope. And alpha i's are essentially just the systems. They represent a polytope of all possible systems. So you can write it this way. You can say this is the where A belongs. So A would be somewhere inside this polytope. And those would be edges of the vertices of the polytope. A1, A2, A3, A4. So you have the situation where you have like, let's say 4 systems, can be 20, can be anything. And what you can prove is that as long as all of those systems are stable, so as long as A1, A2, A3, A4 are stable, A is also stable. Okay. And that is called quadratic stability. Why do we call it quadratic stability? We call it quadratic to indicate largely that it is not Hurwitz stability. Because if quadratic stability fails, so if it is impossible to find proof that all those systems are stable, yeah, and we are talking about, sorry, one second. We're talking about stable at the same time, of course, right? Stable at the same time. So if they are not stable at the same time, for the single Lyapunov function, so if there doesn't exist a single Lyapunov function that proves stability of all of them, then this doesn't imply that A cannot be stable. So this is not if and only if we're talking about Hurwitz stability. So if we can find a single Lyapunov function that proves stability of all of those systems, we've proven Lyapunov stability, and this is called quadratic stability. If it is impossible to find a single Lyapunov function that proves stability of A1, A2, A3, etc. at the same time, it means the system is not quadratically stable, but it doesn't imply that it is unstable in terms of Lyapunov. So this is a more strict condition, quadratic stability. Right. So let us look how we can work with it. So if we can find such S that A times S plus S times A is negative, definite, semi-definite, for all AI, then this system, where this is just A that lies inside this polytope, where those are edges, is also stable. The proof is actually three lines, as you can see. It's very tempting when the proof is 3 lines. So let's see if we can understand it. So first of all, let us consider this derivative of this Lyapunov function. The Lyapunov function, as usual, is x, s, x. And the derivative is a times s plus s times a. Okay. Now we try to rewrite it. No, what do we do here? Well, what we're trying to do is to put S inside the summation. So have like one summation. That is easy. And to put, that's pretty much all we do. We just put S inside the summation. Right. So we have this summation here. So S went under the summation. All right. But we know that all of those are negative definite. And those what do you call them? Alphas are positive. So multiply negative number by positive number, you get negative number. Sum as many negative numbers as you can, you'll get a negative number. This is how we can prove that this is negative. So that's it. Quadratic stability proof. And you can see that this is actually a relatively simple condition, right? Just a ton of very simple LMIs. So for this guy, we have exactly the same situation. We can design this controller for this system, which would give us quadratic stability. And we consider a closed loop system that looks like this. And with that, what is our next step? We consider the Lyapunov equation as before. Right. We get S under the brackets, and we get this sum, where as long as this guy is negative, definite, and this is a positive coefficient, as long as this is true, what will happen is the whole sum will be negative. So we get this condition for stability. All right. But that is very familiar. What we do next is we consider this it needs to be negative. We multiply by p, which is S inverse on both sides, and we get our what we already saw before, this equation. Introduce L equals to Kp, and we get finally this is design. So for quadratic stability, you simply introduce a bunch of vertices AI, and you define a single P and a single L that satisfies all of them at the same time. And then the K would be L times P inverse. So in terms of derivation, this is just levels of magnitude simpler. Unfortunately, the downside is that you would have to list all your vertices. And how many vertices are you going to have? I don't know. 2, 5, 10, 20, 100. For the other stability type, for the other derivation, you didn't need vertices, so you could make it as complex as you want. And this is a big plus, because, of course, you are going to be able to work with systems of arbitrary dimensions. This is very limiting here, but it's very simple. So you have to keep it in mind that this is possible. And the concept of quadratic stability is just nice. Right. So we saw two ways to approach robustness here. Let me just quickly review what we did. We saw that we could just do control design, right, without any robustness for continuous time systems. Very nice and easy. Couple tricks, and that's it. We saw that we could derive a robust controller, but we need to use how many tricks? I mean, first we need this form. Then we need this change of variables, 2 tricks. Then we need this thing, 4 tricks. Then this and this would work at the same time. 5. As procedure 6. Yeah, then divide. Yeah, that's it. Right. This already works, but that is just to check. So 5 tricks for checking. For design, you would additionally have to use this trick, then sure complement, and here you will have to realize that this can be split like this. So about 8 non-trivial steps. Okay. And this one. Yeah. So 9. I don't know. Many non-trivial steps. This, I guess. Here, everything is extremely simple. The answer is just the same as before, but here. So many of the same. Very simple. But here it would work best when you don't have a lot of AI, whereas this guy would work for any dimensions. Right, good. That is what we saw. That is, of course, a drop in the bucket of what LMIs have to offer. So if you're going to study LMI more carefully, you're going to find much more. And it is good. LMI will be able to solve a ton of very interesting problems, including explicit MPC, planning trajectories with robustness, handling various external inputs, guaranteeing that you would have best performance under the worst possible external disturbance, etc. So those things are interesting, and we should take advantage of them. Now you have the tools, the background to use it, and I mean, like from here, you can just start your journey with LMIs. If you want more like additional readings, I would recommend LMI properties in control and stability document on archive, and you can read Amata. he has a lot of very good textbooks. All right, that is it from me. If you have any questions. Right. No questions. You can write me in the chat, ask anytime, or we can ask during the next lecture. Okay. Right. We'll see each other then on Tuesday. Right. See you then. Bye.
Thank you, Professor.
Bye.